Today we are presenting an integrated mechanical intelligence and control approach towards flight control of Aerobat. This work was done by the members of the Silicon Synapse Laboratory at Northeastern University. Traditionally, confined spaces are inspected with ground robots, which are extremely expensive and difficult to operate. MAVs are faster and cheaper than ground vehicles, but drones suffer from ground effects caused by their powerful air jets, making it infeasible for quadrotors to navigate confined spaces effectively. Flapping wing drones don't produce such air jets, so they're quite attractive solutions. However, existing solutions are based on insect flight dynamics, so they don't truly capture the flight characteristics of birds and bats. Here, the insect flight dynamics can easily be described with nonlinear time-periodic problems. This can further be simplified based on the averaging theorem. This can be done because insects have lightweight wings and their flapping cycles are extremely fast, which yields a 2 timescale system. Unfortunately, insect flight characteristics are not scalable and thus cannot copy animal flight. To better understand vertebrate flyers, we are developing an aerial robot called Aerobat at Northeastern University. A robotic bat arm wing is a mechanism called a kinetic sculpture, with computational roles designed to mimic the flying maneuvers of biological bats. The kinetic sculptures allow Aerobat to fold its wings during the upstroke, reducing negative lift and inertia, and thus resulting in a highly efficient flapping gait. Through integrated mechanical intelligence, we can generate complex motions in both wings powered by a single motor. Deviations in the wing trajectory can be introduced with tiny, low-power actuators known as feedback-driven components. FTC locations are obtained based on sensitivity analysis, evaluating the resulting flapping trajectory based on length increments of 2.5%. Small changes in highly sensitive areas can generate large changes in the resulting gaits. The system dynamics can be written in the following way, where XP embodies the vehicle position, orientation, and passive coordinates. YA denotes the aerodynamic contributions, while eta reflects the morphing dynamics governed by computational structures. The dynamics of the kinetic sculptures can be presented here, where the design parameters such as K denote compliance. The last subsystem is the state space representation of the aerodynamic wing interactions. FTCs influence both inertial and aerodynamic contributions. In simulation, closed-loop FTC control maintains a stable pitch angle at a reference of 33 degrees. This demonstrates that the MIMIC framework can successfully stabilize open-loop unstable dynamics in a high-dimensional morphing wing system such as Aerobat. In this work, we presented novel designs for kinetic sculptures and feedback-driven components, comprising our MIMIC framework. This concludes our presentation for today.